either. All right, reductions. Do we need to go into this, or you kind of get this already? Let's go into it. Reductions. All right. Here, in fact, these slides were made first, and for 3101, and they were copied to the halting problem. All right. So here's one problem that these are all the possible inputs to it. These are the yes instances. These are the no instances, right? And here's an easier problem. We want to prove that this problem is harder than that problem. It's hard to prove a problem's hard, so instead we prove it's easy, right? How do you prove it's easy? You come up with an algorithm for it. How do you come up with an algorithm for it? Right, here's an algorithm for this one, here's an algorithm for that one, right? We want to compare their difficulties, right? It's hard to prove that a problem's hard, so instead we prove that this one's easy, right? And by proving it's easy, you come up with an algorithm for it, right? And that algorithm isn't out of the blue. We only need to prove it's easier than the harder problem, right? So we pretend we have an algorithm for the harder problem, which gives us an algorithm for the easier problem. Everybody good? This was on test 3. This will be on the exam. I'm not even saying it may be on the exam. I'm saying I was up until 2 last night. All right. So we pretend we have an oracle to solve the harder problem. What is an oracle? You go up into the mountain, the bush is burning. She gives you the answer, right? Same as a fairy godmother, right? Well, no. No, it's different than a fairy godmother. Different feeling. The fairy godmother is giving you information that you can check, right? She gives you a solution, non-deterministically gives you a solution that you can check. Here, the oracle is giving you an answer that you can't check. The oracle is saying, yes, there's a schedule. No, it's not a schedule, but it doesn't. Well, in this case, if it's a yes, she might give you the schedule. Yeah. But that's why we give them different names, is they have different feelings. Oracles, by their nature, say yes or no, and don't give you a reason why. All right, so here, how do we build an algorithm for our new problem? Right? Here's an algorithm for the oracle problem, harder problem. Here's an algorithm for the easier problem, which we're calling algorithm, because it's an algorithm for the problem that we're going to get an algorithm for, as opposed to the oracle. Right? So, you want to build an algorithm for a problem, the first thing you do is say, yeah? This can be related to the problem that the coloring schedule, right? Yeah, exactly. One of these is scheduling and one of these is coloring. And we did the reduction in both directions, so we tried it in both directions. Yeah. So here, we have this be one of them and have this be the other. So we're given an input to the one, and we in order to use this oracle, we need an input to the other. So what we do is we don't know whether they're yes instances or no instances, but we're given an instance to it. And what do we do with that instance? We do an instance map. We map it, and this is the part, remember I said all I asked for was the instance map. You had to know which direction to go. Sometimes I was so frustrated with wrong answers, I would tell you which direction to go. I would give you hints, right? You need to take an input to this. You know what this problem is. What is its input? You got to take an input to this and give me an input to this. You know what the input to this is. It's written down there on the question, right? In our world, this will be the halting problem. No. In the halting problem world, this is the halting problem. In the NP complete world, this is SAT, right? I know halting and SAT are hard. I want to prove my new problem is hard, right? So give me an algorithm that solves the new problem. I will give you an algorithm that either solves the halting problem or solves SAT, depending on where we're living in the world, right? Depending on whether the solution is arbitrarily large or of a reasonable size. If the solution is arbitrarily large, then it'll help me solve the halting problem. If the solution is small, it'll help me solve SAT. Right? All right, so I do this mapping. You give me an instance to this. I give you an instance to this. We give it to the oracle. Right? There's our instance map. What do we need of this oracle, this map? We need yes instances get mapped to yes instances, no get mapped to no. Why? Because the oracle is going to say yes or no. And if we're doing CARP reductions, we'll give the same answer. Right? I gave you a big hint in the last test. Hey, warning, we're going to be switching yes and no answers. Right? Because we don't need to do CARP reductions, we can do Cook reductions. Right? So, actually, when CARP and Cook defined their reductions, it was probably more for the NP world than the halting world, but the same game applies. All right, everybody good with this? We give the same answer, right? Now, we have to prove that our algorithm works. How do you prove it works? Well, the instance map has to map yes instances to yes and no into no, right? That's what you have to prove. Given an instance over here, I don't know whether it's a yes instance or a no instance. But I have to map it over to something here, knowing that if this is a yes, then this is a yes. If this is a no, then this is a no. Right? And then, why does the algorithm work? Well, if this happens to be a yes instance, then this will be a yes instance. So the oracle will say yes, so we will say yes. And if this is a no instance, then this will be a no instance, so the oracle will say no, and we'll say no. Right? Everybody got that? That's, if you go back, when you leave here, seriously, when you leave here, go back and read the proof for test 3. And that's what it's doing. Right? And I posted on the forum late last night that in my going along, I find little typos and I find little bugs and I fix them. And sometimes I make the answers a little cleaner. Sometimes there was one place the question just seemed kind of dumb. I was like, oh, so I made the question a little better. So sometimes I fix the question. So you might want to download the answers, those answers sometime. All right. So that's it. Everybody good? Here's the code, right? The code for this problem here. I'm given an input for this problem, right? What is it? It's an input to that, and I'm supposed to determine whether or not it has a solution, right? So what do? I take my input, I map it over to an input to the oracle, I give it to the oracle says yes or no, and if the oracle says yes, maybe she'll be nice and give me the solution, in which case she's a fairy godmother. All right? And then, if she says yes, I say yes. If she was nice and gave me a solution, I could take her solution to her problem and map it back to a solution to my problem. All right? So you need to have these solution maps as well. And if we were really going to spend a lot of time doing reductions, we'd have to talk about solutions mapping this way and solutions mapping this way. And we're going to just sort of do it like this quickly. All right? So if she gives me a solution, I'll get a solution. She says no, then she didn't give me a solution. Why didn't she give me a solution if she says no? Because there is no solution. Right? Why is it a no instance? The no instance means that there's no solution. So it would be silly if she said no and then gave you a solution. Right? And then we return her same answer, yes or no. And if we're polite, we give our boss a solution. Yes? Yeah. Here, let's say I'm trying to do scheduling. The oracle does coloring. So I have my courses. Here's my courses. I give a graph. The oracle gives me a coloring. I map it over to a schedule. Right? The coloring gives me a schedule. right? In fact, how do you prove that yes gives you yes and no gives you no? The way you prove it is if this is a yes, then if the graph is a yes instance, it has a coloring. So I map it over to a schedule, which then proves that the course problem is a yes. So if it's a yes here, it's a yes here. How do I do the yes in the other direction? If this course schedule is a yes, it has a schedule. So I do a solution map over to a coloring to prove that this is a yes. It's hard to prove that something's a no. Why is it hard to prove it's a no? How do you prove it doesn't have a solution? It's easier to prove right. I want to prove if I algorithm is yes, if and only if I oracle is yes. Right? It's hard to prove something is a no. So it's easy to prove yes, yes, no, no. Yes, 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 yes here. It would be harder to prove if this is a no than this is a no. Right? How do you prove that? Right? So everybody get this, what we're doing here? And how do you do that? Well, if it's a yes, there's a solution. There's a solution to the algorithm problem. Right? And if there's a solution to the algorithm problem, then I can map it over a solution to the oracle problem. And that's my solution map, which then gives me that this is a yes. And similarly, how we go the other direction. If it's a yes, then it has a solution. And so then I do the other direction solution map so that we get yes to yes. Right? That's what we're doing here. But I'm now giving you more, not less than what's in the slides. What? It depends on the problem. And the coloring gives you where to assign the courses, the time slots. We're going to be doing some examples. I is the input to the problem. We have two problems here. I algorithm is an input to this problem. I oracle is an input to this problem. What's the difference between an input and an instance? I struggle with that one. If I have an algorithm and it has an input x, then you say, what is its input? Its input is the value of x, right? But now I want to substantiate that input. I want to say, well, x is 3. Then 3 is an instance to this problem. I would call x the input and 3 an instance. All right, why do we do reductions? One, to come up with better algorithms for problems. One, to prove that problems are hard. One, to build our map of the world and compare problems. See, these problems are the same. All right, so network flows, right? We can do a reduction. In 3101, we gave an algorithm for network flows that gives us an algorithm for the marriage problem, right? So, what's this? You've seen this page before, right? Now, if we have an algorithm for the oracle problem, it gives us an algorithm for the algorithm problem. So, if we don't have an algorithm for the algorithm problem, we don't have an algorithm for the oracle problem, right? And the other directions, you have to do the reduction in the other direction, right? So we just say one is at least as hard as the other.